Welcome to the video series Programming Animation, a project-based approach. We'll be going through a bunch of projects whose focus is on animation. This is the first project where we'll attempt to write a program that simulate a ball bouncing off angles. So this is the walkthrough video, which means that we'll go through the math and the setup for the actual coding project. Then in the next video we can go through the actual coding. Okay, I'll let you see what it looks like. This is the final product. So this is a ball bouncing off of an uneven ground with a bunch of ground segments. So there's gravity involved and a little bit of damping so that it slows down. If I hit space, it'll reset. So notice that these segments are randomized and this will always work. There it is. So this is pretty amazing. This is it almost seems impossible to write something like this, but the math behind it is actually not so hard, and we'll go through all that detail. Okay, so I am using Java through something called processing, and so I want to at least introduce just real quickly what processing is. If you've done some programming already, then this should be very easy to follow. So processing is Java, and it makes animation very easy. And so let me give you an example of. So when you first learn animation, you would do something like this. So let me kind of show you what it looks like. This is a ball bouncing off just the screen. This is very simple. So here's how you do this in processing. You create these are global variables, position for x and y of the ball, the velocity, the x and the y direction, the radius. Setup is run automatically once to initialize these variables. So here I create the size of the window, I initialize it to be the center of the screen, and the velocity and the radius. And then once that's run, draw takes over, and this will run automatically 60 times a second to create the illusion of animation. So here I'm drawing the background, it's a white background, fill it with the color, draw the circle, then I move the circle a little bit, and then when I redraw it the next time, again running 60 times a second, then it creates the illusion of the ball moving around on the screen. And then there's a couple of conditionals. If the ball hits the right side of the screen, or if it hits the left side of the screen, I change the direction of the ball, so that creates the bounce effect. And then if the ball goes below the screen or above the screen, then again I change the direction, this time the Y direction. So that's it. That's just very, very simple, not a lot of code. Processing makes animation very easy, and so that's just a quick introduction if you haven't done processing before. But this project can be adapted to JavaScript or any other language. Okay, so let me go back to the slides here and talk about how this works. So we're going to take the final project and break it down to three simpler tasks. The first one is we're going to just bounce off of one ground segment instead of a bunch. Then we're going to add gravity and some damping. Then we're going to add a bunch of ground segments through an array of objects. And down below in the description I have the link to my website, which has the distribution code, which basically is a template for these projects, and I left out some code and I have some comments so that you can write the code yourself if you watch this video. Okay, so let's look at this problem. So again, I'm doing something actually very basic. I'm only doing now one segment. So here's what it looks like. So this is one segment, one ground segment, and this is bouncing around and bounces off that one segment. So this is really the heart of the project. If you know the math behind this one, then the other case is just simply a programming project. But this is where the heart of the algorithm is. So let's talk about how to write this program. So let me close that. Okay, so it seems kind of impossible that this works. One of the things that makes it hard is that the ball is bouncing in a different direction. There's an angle to the incline here too, and so it seems like we want to answer two questions. One question is, when does it bounce? And the problem is that we don't know when the ball is going to hit it. It might hit it up here or down here, so we got to figure out when it hits the incline. Then we got to figure out once it hit the incline, how does it bounce? So those are two questions. So we're going to answer this question by looking at the easy case, which is the case where the plane is horizontal. So in this case, I have position x, position y as the center of the bar is a radius, and in processing, the top left corner is actually the origin. Going right is positive x, and then going down is positive y. So it's a little bit backwards, but it's actually pretty standard. So here it is. So how do we know when the ball will bounce if the plane is horizontal? Well, it's very simple. You look at the position, the y position, the vertical position, and the very first time that position is bigger than 400, which is the ground, minus the radius. Again, we're looking at the center of the ball, so you gotta take 400 minus the radius. The very first time that, the very first time that passes 400 minus the radius, then we bounce. And one thing we want to do first is that when it goes past that edge, we want to realign it so that it is right on the edge first. Then we change the direction of the y velocity, which will change the direction of the ball. And so the horizontal case is very simple. Just one simple if condition, and then you just change direction of the ball. Now, how does it bounce? Again, in this simple case, so the bounce here is also very simple. Suppose I have a ball that has a y velocity, so a horizontal and a vertical velocity, so vel x and vel y, and so here's the vector of the velocity. And so when it hits the ground, it bounces very simple. The velocity x is going to stay the same, but the velocity y is going to be negated, just so that it's still going to go right, but it's going to go in the opposite direction. So this bounce is very simple. The angle that you come in is the same angle that you reflect when you bounce off. So the bouncing is also easy in this case. So how about this case, the case where the plane is now inclined? So it turns out that this problem has a very nice, elegant solution. It in fact will introduce a very important idea in mathematics. And we can actually use the solution from the easy case, which is the horizontal plane case, to solve this one. So it turns out that what we talked about earlier about that easy solution will be reused to solve this problem. And so the solution is actually very simple. You literally take this picture and we simply look at this problem differently. And how do we do that? Well, we're going to look at this. We're going to tilt our head so that now the plane is horizontal. So once again, this is the original problem. We're going to tilt our head to the right so that the problem is now horizontal. Then this is an easy problem because this is a horizontal problem. We solve this problem, and then we tilt our head back to get the original solution. So here it is, right? Once again, we want to solve this problem. Unfortunately, the coordinate system for this problem is inclined, so it's not easy. We're going to rotate the coordinate system so that the plane is now level. Now this is an easy problem. We solve this easy problem. This involves finding out when it's going to bounce and how it's going to bounce. So we solve this easy problem. Then we're going to rotate the answers that we found back to obtain the original answer to the original problem. So this is kind of a really nice solution. It's a nice geometrical solution. Okay, so let's look at this, see how this is going to work. So when does it bounce? Okay, so here we go. So I look at the ball position. So pos x, pos y is the coordinate of the ball with respect to, again, top left corner is the origin. This is processing coordinate system. So that's the absolute position of the ball. So here's the ground segment. So gx, gy is the center of the ground segment. So we're gonna view this as now kind of the new origin. Okay, so again, this is the position of the ball, the absolute position of the ball. This is the position of the middle of the ground segment. So we're gonna define dx, dy. This is a vector. So it takes the position of the ball vector and minus the position of this thing. So it'll give you this vector that begins at gx, gy and points to the center of the ball. So dx, dy is this vector right here. So how do you look at dx, dy? Well, dx, dy is actually just simply the coordinate of the ball with respect to the gx, gy point. So in other words, it's the position of the ball relative to this point. And so another way to think about this is that you think of gx, gy as the new origin, and dx, dy is the coordinate of the ball with respect to this new origin. Okay, so now the problem is that dx, dy doesn't tell us when the ball bounces. If you look at this picture, dx dy is kind of at an angle with respect to the incline. So looking at dx dy doesn't help us. It makes the problem very hard if I look at dx dy. And so we're going to take out dx dy, we're going to rotate it. So we're going to tilt our head so that now the ground, the incline is now level, it's horizontal. And so when we do that, when we tilt our head, dx dy becomes dx underscore dy underscore, which is much easier to work with. So again, the original dx dy, if I rotate it, become dx underscore dy underscore, and now this coordinate system, again, this is still the coordinate system, this is still the location of the bar with respect to dx dy, except that now that the incline is now level. And so dx underscore dy underscore is much easier to work with because it's now horizontal and vertical rather than at an angle. So in the rotated coordinate system, dy underscore will tell us when the bar should bounce. So that's the nice thing about this, is that once I rotate it, this is a vertical length segment, so I can easily figure out when the bar is going to bounce in this new system. By the way, because the origin is the top left corner of the screen, dy underscore is actually negative, right? And you can see that because this point is actually bigger than this point vertically. So dy underscore will be negative. And because of that, we want to check to see the very first time that dy underscore is bigger than negative the radius. So again, this is backwards, so you gotta look at this a little bit differently. But because this is opposite, the very first time that dy underscore is bigger than negative the radius, then that's when you bounce. So think about that. And so, okay, so now we want to talk about how to rotate. Well, from pre-calculus, we learned that rotation can be done by multiplying by a matrix. And so, because of processing inverted y-axis, we need to rotate in the negative direction. In other words, we need to rotate counterclockwise in processing coordinate system. So here it is. If I look at this picture here, notice that gx gy is here. We need to rotate around this new origin, around gx gy. So if this is the angle theta, we need to rotate this counterclockwise, which is the negative direction, because again the y-axis is pointing down, so we go in counterclockwise, but we go in the negative direction. So here's the matrix that will rotate in the negative direction, right? The direction where the angle is negative. So once again, dx dy is the position of the bar relative to the middle of the ground segment. I multiply it by this matrix to rotate it to get dx underscore dy underscore, and now dx underscore dy underscore is now the vertical axis, which is the nice axis that we have. And that's basically how we rotate dx dy to dx underscore dy underscore. So how does it bounce? So now we know how when it bounces. So how does it bounce? Well, again, if I look at the original coordinate system where the incline is not level, then bouncing is very hard, because so from this picture, for example, vel x vel y is the vector of the velocity vector, and so as soon as that vector hits the this point, then it's going to bounce. Again, it's going to bounce the same angles that it comes in. So this is easy to visualize, but trying to come up with this vector in the original coordinate system, in other words, look at the x component and the y component, this is very hard. It's hard because, you know, there's an angle here that's involved with the plane, with this inclined plane. So we don't want to use this coordinate system. So once again, to solve this problem, we rotate again. So if I rotate, then the bounce is going to be easy to calculate. So I take the original velocity, vel x, vel y, I'm going to rotate it, just like before, to obtain the new velocity that is in the rotated system. It's still the same vector, it's just now view a different rotated system. So again, if you this is how you matrix multiply. You multiply vel x with cosine theta plus vel y with sine theta, and you do the same thing for this second row. So you matrix multiply to rotate. So here's the picture. After I rotate it, vel x vel y is still the same velocity, but now it's rotated and everything is horizontal and vertical, so it's easy to visualize. So in this new rotated system, it's easy to bounce because all we have to do is, because this is now level, to bounce, this is the easiest solution. To bounce, we keep the same velocity x and we simply negate the velocity y. So this is a very easy way to bounce because the system is now horizontal. So the reflective velocity in this new rotated system is vel x underscore and negative vel y underscore. So this is very simple bounce. We're just negating the vertical component. And then we got to take this velocity and we have to now rotate it back to obtain the original answer. So I take vel x underscore and negative vel y underscore, which is the bounce velocity in the rotated system. I rotate it back. So notice this is the inverse matrix. This rotates this back the other direction, and I get my final reflective velocity in the original problem. So once again, right, I rotate the velocity x plus or y to get the easy vel y underscore vel x underscore. I negate it in the easy coordinate system, then I rotate it back to obtain the original bounce velocity. So that's it. That's a pretty, geometrically is a very simple solution. Let's look at the distribution code. So again, this is available on the website. So here I just it's a template for the entire project. I declare all the variables that kind of match up with the video. GX, GY is that middle point. Rotation is the angle of the ground segment. Length is the length of the ground segment. And so you can fill out some of those yourself. So again, all the comments here helps you fill out the code. And so for example, there's a nice distance method that you can use to calculate the distance between 2 points. You can use that to find the length of the ground segment, and then you can use the inverse tangent version 2 to find the angle of the incline segment. So this is the setup method. This is where you initialize all your variable, and so to find the length and the angle, we simply use the distance method and also the distance formula method, and A tan2 is the inverse tangent version that allows you to find the angle of the incline plane. And so then in the draw method, we just have to write a few methods. So displaying the bar, so that's very easy to draw that. Move the bar, and then check against the wall collision, the top wall, the right wall, and the left wall. And then the heart of the algorithm is this right here. This is the collision against the incline plane, and that's where everything goes. So there's only a couple of lines of code here, right? Using the ellipse to draw it. Moving the bar is just adding the position, adding the velocity to the position. You can also add gravity to this part, which we'll talk about in a second. And then this is checking the wall collision. This is the easy one with everything's vertical or horizontal, but the heart of it is this one. This is where you check the incline collision, the plane collision, the bottom plane collision. So again, you compute the x dy from the slides, and then you find the cosine, the sine of the angle. You can use COS and SIN for those methods. And then this is where you rotate dx dy to the new dx underscore dy underscore that we just saw. We're also going to rotate velocity x, velocity y to the velocity x underscore, velocity y underscore. So you can look at the video again for the formulas for those. So this is rotated, and then now once we rotated it, bouncing is very easy. And so again, this is what we saw in the slides, that if this thing is bigger than negative radius, then we realign the bar so that it's on the edge, and then we negate the velocity, negate the vertical velocity. We negate this velocity to get the bounce. Then we take the whole thing, we rotate everything back to get the original answer, and then we move the bar to update the position of the bar. So this is available on the website, so feel free to kind of try it out before I show the actual solution in the next video. But I want to go back and talk about some adding gravity and damping. So just a couple of quick definition. Velocity is the rate of change of position over time. So when I say velocity is 5, I mean 5 pixels per frame, and by adding velocity to position, I'm moving the bar. So this is position, change in position over change in time. So this is moving the bar. Now to add gravity, we need the idea of acceleration, which is the rate of change of velocity over time. So this is change in velocity over change in time. So if acceleration, for example, is 2, then that means that every frame my velocity changes by 2, and so it's simply taking the old velocity, adding the acceleration, and then now that my velocity is changed, I can add it to my position to move the bar. So it's just really these two formulas that give you the illusion of gravity that we saw in the in the final version of the project. And so once we get the ball to bounce correctly off an angle, adding gravity is very easy. You initialize the vertical velocity to be 0. So this is like dropping a ball. The initial vertical velocity is 0. You give the initial x direction velocity some small number, and then we just initialize the gravity to be something small because we are moving at 60 frames per second. And so really the code is just basically adding gravity to the vertical velocity. So this is adding acceleration to the velocity, and then adding the velocity in the y direction to position in the y direction, and then adding velocity in the x direction to position in the x direction. So this is changing the velocity, and then this is changing the position. So this is all you need to do to add gravity. And then damping is the idea that when you hit the wall, it should bounce back but slower, so that way create the illusion of slowly losing velocity as you are bouncing around. And so without damping, right, the very first time the position of x is bigger than the width of the screen minus the radius. So if I go past the right side of the screen, for example, and I don't want to go past it, so I want to realign it so that it's on the right edge of the screen. By the way, width in processing is the default width of the screen once I create the size of the screen. So once I realign it, then I can change direction by negating the velocity. So this is no damping, meaning that when I bounce, I simply change direction, and it's the same speed. With damping, it's very simple. Which all we do is that instead of negating it, we negate it, and we also multiply by 0.8. So that means that the velocity that after I bounce is reduces by 20%. So now 80% of the previous velocity. So that's how you create the illusion of damping or slowing down the ball. And then finally, to add multiple ground segments you have to use object-oriented programming. So if you haven't done that, you can look at the link below for some tutorial for that. But we do need to create an array of ground objects. So this class right here is the ground object class. It has x1, y1, which is the top left corner of the ground segment. x2, y2 is the segment on the right side of the ground segment. X comma y is the center of the ground, which is just the midpoint of the endpoint. So that can be calculated easily. And then length is the length of the segment, and rotation is the angle of the incline. So it's just this angle right here. So if you have this ground object, then I can create an array of these objects, and then we can do the final project where it bounces off all these ground segments. And so again, this requires some object-oriented programming. You create an array of ground segment objects, and now it's very simple. You do the same algorithm, but you apply it to every ground segment. So you do a for loop, and you check the ball position with every single ground object, and you apply the same algorithm to each of those ground objects. And so whenever the ball hits one of the ground object, then we apply the algorithm to only that ground object. And so we gotta make sure that the ball is within the left and the right bounds of the segment. And then we apply the algorithm. And so in the code, the template, the distribution code, I have additional comments that will clarify this. Okay, so let me show you that distribution code. So this is the final project distribution code. So you create a ball object. So there's a ball object here. It has a position, a radius, velocity x, velocity y, some gravity. Here's how you initialize your variables. This is the constructor. Displaying the ball, move the ball. You can add gravity here if you like. And then check wall collision. So this is just like before, but now it's just the vertical and horizontal walls. And then there's the check incline collision. So this is the same thing as what we did earlier in the last project. It's just now we put it in the ball object class. So everything here is the same as before. But one small thing is that we do make a small change here where when we check against the incline collision, there's only one ball, but there could be many ground objects. So when I check incline collision, I check it against each of those ground objects. So this now takes an object which is one of the ground segment from the array, and then so this applies to one ground segment object. So here's the ground segment object. Again, these are the variables that we saw earlier in the slides. Here's the constructor, and that's actually it doesn't do anything. It just initialize that one ground object. And then in the actual main method, in the main driver class, you can set the number of segments here. You create an array of ground segment objects. So in this case, I create 20 segments, for example. Setup, just initialize everything. So again, all those comments help you write it. In fact, I even leave you the code so that this will draw the actual ground, the ground with the other segments all together. So this will create, this will initialize all the ground objects. And then when you draw it, I left again here some comments, and then I have the code here to use begin shape and end shape to draw the actual ground. And so again, there's some tutorial that I have on drawing with processing, but if not, you can look these up. Processing is very easy. So begin shape basically means that you're going to draw, you give it a bunch of vertices. This will draw the ground with those points as vertices. So we have a for loop for all the vertices of the ground, and then we close it to create that red ground object. So this is drawing the ground, and so that code is included. And then and this is key press. So again, processing is so simple. It can listen to key press very easily using the key press method. If I press the space, it's going to cause setup to initialize everything and start everything over again. Again, there's some randomization here, right? We're going to randomize the height of those ground segments. But that's basically it. That's kind of the final project. And so feel free to kind of work with this first. Try to see if you can make it work. And then in the next video, we'll talk about how to write this completely. Okay, I want to tell you some cool math context to this solution. Turns out that this rotation change of coordinate trick, the idea of you used to rotate, you solve the problem, and then you rotate it back, is actually a very important idea in mathematics in general. In linear algebra, for example, this is called change of basis or a coordinate transformation. In group theory, this is called conjugation, but this idea is very important in mathematics. And you might have seen it even in linear algebra or even just regular pre-calculus from high school. You might remember that two matrices are similar if there exists an invertible matrix Q, so that one matrix is Q inverse times B times Q. So you might remember this from linear algebra or pre-calculus. But this formula should be very familiar to us because this is exactly the formula that we use to solve our problem. This is exactly the algorithm. So if I let A be the hard bouncing problem, the bouncing problem with the inclined plane, then this formula tells you how to solve the A problem. You first rotate so that the ground is level. So that's Q. Q is the rotation, the counterclockwise rotation matrix. Then we solve the easy problem, which is B. That's the bouncing on the horizontal plane problem. And then when we solve that, we just rotate it back, which is Q inverse, to get the original answer. So that's exactly the heart of the algorithm that we just went through. So here are a couple of cool examples. And the first example is kind of silly, but it illustrates this concept of coordinate transformation to change a problem that's hard to one that is easy. So suppose that you're really good at drawing horses, and so you can draw a horse very nicely. Let's call this operation B. This is the easy operation. This is the easy problem. You can draw horses very easily, and this is like bouncing on the horizontal plane. Now, what if someone asked you to draw the horse, but in this orientation, upside down? Well, if you would try to draw this upside down, that would be a very hard problem, right? So let's call this operation A. And so, of course, we don't want to. So this is how we draw. Well, if I can draw horses standing up, I can draw an upside down horse by doing this same operation. So let's take the piece of paper. I mean, this is an obvious solution. You just rotate it, which is Q. Then you draw. You know how to draw this on the regular direction. Then you rotate it back, and that's how you draw an upside down horse. It's just simply using this. You change the perspective so that the problem is easy, then you just unchange it to get the original request of drawing a horse upside down. Yeah, so this is silly, but it illustrates this idea of what we did in our problem of tilting our head so that the problem is easy and then just rotating it back. But here's kind of a cooler solution that uses the same algorithm, and this is what I mean when I say that this idea is very important in mathematics. So suppose that if you've done Rubik's Cube before, you might be familiar with this. If not, this is very easy to understand, even if you've never done it before. So here's the Rubik's Cube, 6 sides, right? These are the projection. So for example, this is the orange face on the left side. There's a blue. This is a red, white, blue. So these are the projections, and these are the three sides that you see. So suppose that you're really good at one algorithm, and that algorithm is a three-corner rotation. In other words, I can take this point, this corner, I rotate to this corner will go to this corner, and this corner will go back to this corner. So this is called a three-corner rotation. You rotate those three, and then everything else remain fixed. So that's the key, is that you rotate three of them, the rest of the cube is unchanged. So let's call this algorithm B. And suppose that you're good at this algorithm, you know how to do this algorithm, and that's an easy algorithm. Now, what if someone asks you to do a three-corner rotation, but this time they want you to rotate this corner, the top left corner here, down to the bottom, and they want you to rotate this corner to this corner, and then this corner finally back to this corner. So this is still a three-corner rotation, but you're rotating three different corners. And so this is a harder algorithm. Let's call this A. By the way, if I rotate these, then I actually solve the cube. So how do I use the easy algorithm to solve this hard algorithm? It should be kind of obvious now, because again, I know how to rotate these three, keeping everything else fixed. Now I want to rotate these three, so the solution should seem kind of obvious, because all we do is take the original. So again, I know how to rotate these three, so if I can move this corner up here, I can apply my algorithm. So that's what I do. I rotate it. So that means I take the back face here and rotate it clockwise, so that this corner goes on top. That's what happens here. So now this corner becomes this top corner, and now I can apply my algorithm of rotating these three corners, fixing everything else. So that's my easy algorithm. So that's applying the algorithm. And now I just rotate it back, Q inverse, and I just solve the problem. So that's so again, this is kind of something we do in Rubik's Cube, but it illustrates the same principle of taking a hard problem and changing it by rotating it, so that you look at it differently and it becomes an easier problem. So that's the walkthrough of the project. The original idea is actually done by Keith Peters. His book on HTML5 animation with JavaScript actually go to this project, and I just changed it to processing. In fact, processing.org, you can go there to download processing, but it has examples, and this is actually also one of the examples from the website. The picture I used for Rubik's Cube is from Ryan Heist's website. He has really great tutorials on Rubik's Cube. So in the next video, we'll go over the solution to the project. But I hope you take the time to kind of look at the distribution code and at least try to code it yourself. And if not, we'll go over the solution in the next video. If you like the video, then please subscribe and like. And there'll be a bunch of these projects in the future. So hopefully you can come back and just the focus of these is there'll be some math in these projects, but hopefully they're accessible. Okay, thank you.